which is one of the most common, one of the most well-studied theories for learning. Maybe the most accepted, I would say, even though in recent years it has gone less out of favor and more in favor of online learning, which was the majority of the lecture of the course so far. But still, I think for in many papers, in many studies, this is the paramount, the major theory of learning that people use, or the notion of learning that people use. Another name for it is PAC learning theory. This stands for probably, approximately correct. And I will explain why probably and approximately. You need kind of both disclaimers. Before I forget, anything administrative that I need to announce, exercise has been released. Exercise 3 has been released, I believe, on Tuesday. And you should have gotten an ed notification for that. And the deadline for that is Tuesday? 2 weeks. Is that on break? It's not on break. After break. Tuesday after break.
During break.
I don't know, Chris says during break.
Oh, during break?
Yeah.
No, let's do it after the break. Okay, so after the break. 1 week after the break on Tuesday. I don't like it that, I never liked it that I had things to do on the break. So you can relax on the break, and after the break you can resume. Any question about administrative issues or anything we've done so far? All right, so let's start statistical learning theory. That's the topic for today. This is a theory that was designed from the very beginning to encompass what it means to learn. And the reasoning behind it is developed by many people, by statisticians, and later by Vapnik and Chernovakis, who are also statisticians. And it's different. It's different style of theory than what we have talked about. I motivated online convex optimization starting from prediction from expert advice, which I think is a very intuitive way to motivate it. So you have a problem you want to solve. Maybe it's a toy problem, but you can see it's kind of a building block for maybe more complicated things. And indeed, we took it from one special case to more and more general paradigm that can encompass many different decisions and many different types of problems. And that's how it was built also historically. So theory of online learning and theory of online context optimization were built bottom up. This theory that I'm going to describe today was built top bottom. It was, for this reason, it's more widely taught, I would say, much more widely taught than the way I taught you. But I would say it's accepted nowadays that it's not as very, I don't want to say successful, but I will say successful. In my opinion, it's not very successful. And I will explain why. I think that, and the kind of rigorous, precise reason why this model doesn't give too much insight into what learning is, but that's what we try to do. And still there is a lot of beautiful mathematics here and theory. And the reason the way I'm going to do it is by defining the constructs of it. I will guide you through the thought of how this was developed and what were the thought processes for developing the theory. And then we'll see the main conclusions of it. So the thought was, I have a learning problem. Let's say I'm trying to classify digits. You all know MNIST, right? Dataset MNIST. That's kind of the first data set you start working with. And you have all these images that are 8 by 8. And then maybe this is blacked. And if these are the dots here are blacked out, then this is the digit 1. So this was a very popular data set in the early days of machine learning. It was collected by Yann LeCun. He's the pioneer of deep learning. And what does it mean to learn on this data set? Well, you can say, maybe I collect a lot of images. So I can collect from, at the time, this was distributed by the patent office, I believe, or standards, some government office, which has to do with standards and patents. And they collected a whole lot of these images, and the idea was to be able to sort mail automatically and identify the zip code automatically and therefore sort mail, which today seems very easy. But at the time, it wasn't very easy, so they collected a whole lot of these images in something that we call a train set or a sample. And then the idea was, okay, I have a training set or a sample. From that, I can build a machine, which for today we're going to call a hypothesis, that maps these images to the digits that they actually represent. In the case of MNIST, there are 10 digits, and I don't know how many images that you should classify into the 10 digits. So a bit more formally, we have data that is given by a distribution over x cross y. And x is the features, these are the features. The data, these are the labels. So for example, for the MNIST data set, the features are the 64 binary bits that represent the image. And then the labels are the digits 1 to 10. And another example would be maybe this example 1. Maybe I'll give you another example, for example 2. Text classification. It's amazing how trivial the problem looks to me now. At the time, it was a difficult problem. In text classification, you have documents. A document, you can represent as a vector in 0, 1 to the vocabulary, vocab. This is called the bag of words representation. So which means you put a 1 there if the word appears in the document and 0 otherwise. And then maybe you want to classify it. So you want to given doc V, you want to say, is V about econ, for example? Is it an economics document or not? You can ask that kind of question. So for this example, you have data which are documents, and you have labels which are 0, 1. In this case, I want to classify them. Are they about economics or not about economics? And the data is given by distribution over all these documents that you can sample in the world. So this is how we model data. Data is points, x, y. So x, y are data points. There exists a concept that we want to learn. What is a concept? A concept C is a mapping from x to y. So we assume that the data satisfies y equals c of x. There exists a mapping from input to output that determines the labeling. So for every document, there is some concept. The concept is our human understanding. Is it an economics article or not? Or there is a mapping, there is a ground truth that whatever the person wrote on that character, on the letter, that's the digit that they actually wrote, and that's the true concept. Maps images to digits. Now, so these are the main constructs. How do we access the data? So that's also important, data access. So we can sample. We can sample x, y from the distribution. These are known. Unknown, and it can be completely arbitrary. Arbitrary distribution. There's no restriction. unknown, it's arbitrary, but if I sample another data point, it comes from the same distribution. It cannot come from a different distribution. This is different from online context optimization because
Functions can change arbitrarily.
exactly, right? So the labels can change. There is no underlying distribution. It can be anything. From one iteration to the next, things can change arbitrarily. Yeah? And what is the goal? So the goal here remember the goal in online learning was a bit tricky. I talked about prediction from expert advice, and I didn't want to make these assumptions about the distribution and data access and so on. It was more general in that sense. Then I needed to define a tricky goal. But here I think the goal should be much more obvious. So if you define the model this way, what should be the goal?
Minimize your loss on the data set.
Okay,
Expect loss on distribution.
very good. So the goal is to design an algorithm that can sample data and for any sample it creates and returns a hypothesis that's close to the concept. So let's say a bit more precisely what I mean. What is the hypothesis? Hypothesis H is also a mapping from X to Y. Maybe the algorithm saw a sample of size. So algorithm, it's sample, S is a sample, and that's a mapping from X to Y. S is a sample from D of size M. And it's a set of pairs X, Y, so it has seen these N pairs. And then it generates a hypothesis from X to Y. And the goal is to minimize error of age, which I define to be, as Bogdan was saying, expectation x comma y from the distribution, age of x not equal to y. That is the goal. I want to minimize this error. This is if we have a 0, 1 or some kind of discrete labels. You can generalize it to a loss function. So if I have a square loss function, Rafael, what's going on? Why are you not with us? Come down. So, you're so far away. So you can make this into loss, right? Loss of age of x, y. And as Elijah just asked me, this can be, for example, square loss or any kind of loss, but between the true label and my prediction. Yeah.
What's the difference between A of S and H here?
No difference. I mean, age is just a general name for hypothesis. A of S is a particular hypothesis that's generated by an algorithm that sees S samples. But it's the same object exactly. And both of these are the same object as a concept, because they're all mappings from label from feature to label. Yes?
If we're thinking about this as like typical machine learning, like we should interpret S as like the training set, right?
I didn't hear, sorry?
If we're thinking about this as like normal machine learning stuff, like we
Yeah.
should think about S as the training set.
Yes, correct.
Like what's preventing us from, like do we get to choose S or is S given?
The way we access data, this is the data access model. We can sample. You can choose as many as you want. You can sample more and more and more.
Like what would stop someone from just constructing, like you take S to be all of X and then.
Well, maybe it's continuous, maybe it's infinite, maybe there are too many, maybe computation complexity considerations. And clearly, the less samples you take, the better your algorithm is. Right? So that's called sample complexity. We'll talk about it. So sample complexity, in fact, let me say that now. So what is the sample complexity? number of examples needed to get epsilon error. And with high probability. I will define it a bit more rigorously soon, but this is a non-rigorous definition. So I have here, I want to get low error. Error is what's happening here, and I want it to happen with high probability. Why do I have the probability? Why do I need this probability thing? Why can it always happen?
Because you're sampling from a distribution.
That's
could
right.
get really bad samples.
I could
Or the
sample,
same
maybe
sample.
I could sample the same exact sample even if I sample a trillion times, okay? It's possible. It's a very low probability, but it can happen. That's why I need to talk about probability here. In this model, it's a probabilistic statistical model. That's why it's called statistical learning theory.
Are we recording?
Yeah, I believe we are. Yeah, we are recording. But you can ask me, you're already here.
You didn't do that hello YouTube audience.
Okay, yeah. Hello, YouTube audience. Okay, good, yeah. I was a bit lazy with the YouTubes, but they're all online right now. So I uploaded everything until now. Questions? Yeah.
Shouldn't S be distributed according to the product distribution, since it's M samples?
Yeah, it is. It is. Yeah. Yeah. But I denoted it like this, S from B. So this is shorthand, meaning that every single item in S was sampled according to B, according to my data access model. Okay? So now, the first question I want to ask is, what is learnable? So, what is learnable? What problems are learnable in this model? And any guess so far? Yeah, Joshua?
Maybe you need some smoothness restriction on the concept.
Well, I don't want to do that because the concept, you're right, but I don't want to go there because what if what I want to learn is non-smooth? Maybe it is the digits or it's some arbitrary thing. I want to learn to map your face to a name, for example. That's not a smooth function, or I don't know what to say, you're all very different and so on. It's not clear to me what smoothness means in this situation. So I don't want to restrict my concept. Does it make sense? Restricting the concept is not a good idea. The concept is given by nature. Maybe I restrict the algorithm or some other things, but not the concept or the guarantee. Yeah, Colin?
Like independence or uniforms?
Oh, that I assume. They are sampled independently. Completely, I assume that. Yeah. Yeah?
I would say every time you sample the same X from the distribution, it always has to map to the same Y.
Oh, that is by definition. So there is a mapping. A mapping means it's a one-to-one and onto bijective map. Well, it doesn't have to be onto, but it's a one-to-one. So a function is defined by, for every X, it has a single Y. It's not, cannot map the single X to many Ys, right? That's not a function. So it's a mapping, yeah. That's, I assume that, yeah?
The concept is supported on the data set or on the data distribution.
On all possible X.
In
But
some sense, not on all possible X.
I mean, in some sense, it's easier if it's not. What if the concept is just maps a single X to Y, and that's the only distribution is only there, and that's all that happens, So X, I only have one person, Elijah. This is the face I see. His name is Elijah. That's it. There's nothing else. It's easier for me to learn in some sense, right?
But if it's disjointed, you couldn't ever learn it, right? If the concept you need to learn something where the data set doesn't
Yeah.
actually sample that X, could you learn it?
Well, learning, so you see, the learning here already contains both the concept and the distribution. So the concept is contained by the very fact that I have Y here, this is C of X, and the distribution. So it takes into account both of these. This is called the error, or you can think of it as generalization error. It's also called the generalization error. This means I took some sample, it's not everything, I didn't see all of it, I saw some small bit of it. And I want to say, look, no, I have low error. That's what I want to say. And my first claim here is, I didn't define it well enough. So maybe it's tricky to see. I think Joshua had a bit of an insight into that. But there is something missing from my definition. Something is pretty bad. And what is missing from my definition? Yeah,
The possible hypotheses,
okay, that's good. Why do I need that? Why do I need to talk about that?
because otherwise your hypothesis could just exactly match your concept.
I wanted to make my
That's-
concept. That's a good thing.
It's possible, but it's just you need to parameterize it somehow.
Why?
Uh,
You're right. You're absolutely right. Why?
I can't think of a way to solve a problem otherwise.
Yeah, Edward.
Maybe depending on the problem, you might need infinite data points to learn hypothesis that is not parameterizable.
Mm. I don't think, I wouldn't say it's exactly that, but you're right what it said. Wait, Joshua?
If you don't have a parameterized family of like hypotheses, you can't do any descent methods in order to learn the parameters.
You're talking about optimization. I'm not, look, my main beef with this model is that it doesn't give me efficient algorithms. That's a huge problem, okay? I'm gonna go into that in depth. And in fact, renders it useless from my perspective, completely useless. But it's not, I'm now talking about existential learning. You know, people thought we can separate it out. The learning, you know, in the kind of Platonic space, it exists as a beautiful concept, and indeed mathematicians were happy about that. I claim that's completely, you know, detached from reality, detached. And I will show that to you, provably, I hope. Yeah?
If you don't restrict the class of mappings you can learn, you're going to overfit to the
Good.
data that you
So what
see.
does it mean? Good, that's, you're right. What does it mean?
Well, one thing you could do is you could say, okay, I see every input X.
Yeah,
I'm just going to say if it's X,
Yeah.
then it's Y.
very good, very good. So let me make that formal, okay? That is exactly correct. What does overfitting mean? In fact, what can I do with my training set that will help me generalize? The best thing I can do is, for example, try to minimize the error on the training set. I've seen some examples. I can minimize the error on it. That makes sense, right? I can say, okay, let me find a hypothesis that does great on the examples that I've seen. So let's say that I have some M examples out of this distribution D that's supported over 2M. So even I've seen half of my universe. And then I've seen this is 1, this is 0, this is 1, 0, and so on. But these I haven't seen. Okay? Now, if all hypotheses are possible, maybe I will say, okay, my hypothesis, oh, you've seen this is 0, this is 1, this is 1, this is 0, and anything else say 0. That's a perfect hypothesis on the sample that I have seen. But it tells me nothing on things that I haven't seen. For example, or another example, let's say I know all of your names. I know all of your faces and all of your names. If I see another student, it doesn't tell me anything. So I don't know. I don't know the name. I know your name, but I don't know, because it's all possible. I have too rich of a hypothesis class that I'm considering. Yeah?
Yeah, I thought like the measure against this was by talking about sample complexity, like to prevent overfitting, like and overfitting actually working. That would be when the training set is too big, and the sample complexity make sure that's what happens when we care about it.
That is correct, but if my sample complexity is see everything, that's not a useful measure of learning.
Yeah.
Right? So suppose my universe consists of M items. If my sample complexity is M, does this really mean that I learned something? In some sense, generalization is mute here, right? Generalization is interesting if you see few examples, you're able to generalize from them to a much bigger concept class.
Like then why do we need to restrict H if we already care about sample complexity and that stops us from overfitting, right?
Oh, this is an example of overfitting. I don't restrict age here, and I'm just saying there is a finite universe that if, so here is the claim. This is actually an interesting, the lecture today is philosophical, okay? I'm doing Greek philosophy I'm doing today. This is not a very practical lecture. It's about theory of learning, which is not algorithmic. So bear with me. So this is called no free lunch theorem. And the theorem says the following. I'm just going to give it to you, provably say what I mean. So it says I have a considered domain I'm going to say formally what Elijah said informally. Let's say the size of this is M. Then, for any algorithm, doesn't mean what the algorithm is. There exists a concept and distribution such that the following thing hold. So one, the error of the concept is 0. So concept can generalize perfectly. Oh, I should say. So for any algorithm, there is the concept distribution such that for sample size M over 2, so even if I've seen half of the domain, which is huge, N2 with probability at least 1/10, the error of this hypothesis that the algorithm returns is at least 1/10. Yeah.
Sorry, why do you need the error of C to be 0? Isn't that?
I want to say it's true by default, yeah, but I want to emphasize here that this is a learnable problem in theory. It's possible to learn it. Okay. But it is true by default, you're right. Yeah.
Is the 1/10 like a special number?
No, you can be made, I think it can be made 1/4. Yeah. You'll see it's a simple thing. So I'm going to prove it by probabilistic method, which some of you I know are going to Noga Alon's class in math, and it's a very simple application of that. Yeah?
What do you mean by error on C? Like error on AS is just like on like.
So error of any hypothesis is defined to be like that. I sample points from the distribution, and I measure what's the probability that the error of the hypothesis is different from the label. And C is equal to C by definition, so this is 0. But I can measure the error of C. You could think of the reason I have the extra generality here is because you can define error in a noisy setting, where maybe you have a concept, but maybe you flip the concept's output with some probability. So you have some noise in the data, and therefore no concept is perfect. Okay? But here I'm saying something stronger. There is a perfect concept, it's 0 error at all, and yet whatever algorithm, doesn't matter which algorithm I'm going to use, it's going to have high error with high probability. Yeah.
You might be getting to this after you prove this theorem, but the fact that you can construct a distribution such that you get this result may not be a bad thing for this form of learning, right? Because the distribution could be arbitrarily complicated, it could be something that you'd never see in practice.
But that's not what's going to happen here. So you're right, but that's the correction is going to be simpler than limiting the distribution. It's going to be what, I forget who said, you said over there. Your name again?
David.
David, what David said. So I need to restrict my hypothesis class, not the concept. So actually it's a very, yeah,
You have to look on the error.
On the error, yeah.
If we did not have that, does it mean that the problem would be too trivial to solve?
not necessarily. I mean, you could have a very hard problem that for some reason one example somehow gives you a lot of indication of what happens to the rest of the distribution and so on. It could be. It could be that there is a computational problem that if you solve on the first example, it's an NP-Harmon problem. Now you solve it, you kind of immediately know what every other instance the label is going to be. So you could have difficulties arising from different sources, not necessarily from the statistical source over here. But this is a statistical lower bound. It's actually a very simple lower bound. And what it's saying is, it's saying something very simple. I mean, let me just show you. So the proof, as I'm going to consider m examples, and then let's say the labels are 0, 1, uniformly at random. So this means I pick a concept from all possible concepts uniformly at random. That's what it means. So let me define some quantity which I'm going to call Q, which is the expectation over all concepts from sample to 0, 1. Sorry, from all feature vectors to 0, 1. Then I have expectation over my sample from D to dm, error of the algorithm applied to the sample, so this is somehow my expected error of my algorithm applied to the sample that I picked. When I pick a sample uniformly at random from the distribution, and I consider all possible concepts that can happen. Yeah?
Shouldn't it be like m by 2, m divided by 2.
What did I write? Oh, yeah, m by 2. You're right. Thank you. Well, I saw half of the work. Yeah. And I claim that this Q is bigger than 1/4. And because it's bigger than 1/4, and this is a non-negative random variable, with probability at least 1/10, it's bigger than 1/10. Okay, so you can use Markov inequality. So that answers your question, Jerry. You can play around with the numbers here to make it a bit tighter. It doesn't matter so much. So learnability means I can get arbitrarily low error. I'm not stuck at 1/10. That's what prevents learnability in my model. Yeah.
I'm sorry, what do we mean by expectation over the concepts?
So as I defined it, the concept, these are the labels assigned to the examples. And as I defined it, I labeled them uniformly at random. So this means the concept is a random variable which is chosen uniformly at random. So I'm showing some probabilistic statement. This will mean, by the probabilistic method, if I show you a random variable, it's non-negative, and I show you expectation is bigger than some 1/4, it means there exists a concept that will make this bigger than 1/4. Okay? So that's called the probabilistic method. You show the existence of a creature by randomization. The probability of event bigger than 0 means there is this event is non-vacuous. It can exist. It's a very simple application of the probabilistic method. And now let me just show that it's bigger than 1/4. So this Q is as I wrote it, is equal to, I have expectation. I can flip the order of sample and concept, and I can condition on the sample being from the sample, the exact example. So this error is the probability, or if you will, expectation over x from the sample, A of s equals y. That's by definition. Right? So I can write expectation over s and x, expectation over the concept, A of s of x equals c of x, given x in s, times probability x in s, same thing. So this is the law of conditional probability. Conditioning x not in S, probability x not in S. So probability of x in S is what?
1/2.
Yeah, 1/2. Because I'm choosing uniformly at random, right? So I picked my sample size is half. So this is 1/2. And now so error is not equal to. So this is 0. If my point is in the sample, I got it right maybe, because I picked, I don't know if I got it right or not, depends on the algorithm, but maybe I got it right. So it could be that I got everything correct. But if my point is not in the set, then what is my error?
1/2.
Yeah, 1/2. Because
Because it's just random. Like
exactly. So whatever my algorithm does, the label going to be sum of it is at least 1/2. So this is bigger than, this can be maybe 0, I don't know. And this is bigger than 1/2 times 1/2, which is 1/4. Okay. So because of this, by Markov, the probability that a concept has error A, probability what's written here, E of S, error AS, bigger than 1/10 is at least 1/10. Okay, so because everything here is non-negative, I can apply Markov inequality. Right? Because otherwise, if this is less than 1/10, then my whole expectation, this is a bounded random variable between 0 and 1, it will be smaller than the 1/4 that I have. So what I've showed you, is this okay? Is this clear? Take a minute for a question, maybe. Yeah.
Sorry, I missed the part where you, like, where'd you get the 1/10, 1/2? This is 1/4.
You're asking why it's 1/2? Okay. Well, the probability x is not in the sample. If I sample uniformly at random, that's 1/2.
Yeah.
And then what is the expected error of the point that I chose, given that it's not in the sample? I've never seen it before. If I've never seen it before, my algorithm has no idea what's going to be there. So if I look at all possible algorithms, right, doesn't matter what they are, and the label is 0, 1 uniformly at random over there. So it's going to be 0, or it doesn't matter what the algorithm says. It's a random label. Yeah.
Okay.
Okay?
Thank you.
Sure.
Why is it called the no-free lunch theorem?
I know, it's a silly name. I mean, they were trying to be funny. I guess it means that basically if you don't restrict the hypothesis class, you cannot really learn. That's kind of the meaning of it. So the model as it is no good. This is a philosophical kind of theorem. It's not a hard theorem. And all it says intuitively, you got it right, David got it right here immediately. So what if I have this, here is an hypothesis. I want to classify objects in the real world. Oh, someone thought it's a bottle, this is a bottle, this is a cup, this gives me nothing. If I see something else, I have no idea what it will be if I don't bias my hypothesis class, if I don't restrict it somehow. That's what this theorem is saying mathematically. Yeah? Questions? So then, my conclusion is this is no good, as it is. But here is the correct, yeah, Karen?
Sorry, I was just asking you about why getting us out, or restricting the hypothesis helps us with the
Well, I didn't show you why that happened, why the restricted hypothesis class helps. I didn't show that. All I showed is that If I don't do that, I don't have a good model. That's all I showed you. Okay? So I showed, it's not even clear it's worth, anything I'm doing is worth anything, but I showed you some approach which is no good so far. Okay, so I proved to you it's no good. Yeah.
But don't we have to restrict the concept, not the hypothesis?
It's less natural in my opinion. It's less natural because the concept is given by nature. I can't restrict it. It's, colors in the world or whatever, something that happens in the world. It's not under my jurisdiction to say I only look at particular worlds that are easier for me. That's kind of, I don't like this philosophy. The philosophy is, whatever the world is, I'll be able to do something with my tools. And my tools are my hypothesis class. So that I can restrict, my own capability, but not the world model and power.
But
Make sense?
We have to believe that the world is structured so that we can.
No, well, kind of. So when I restrict the hypothesis class, why am I restricting it to some particular domain, let's say neural networks? Because I believe neural networks are very powerful and they can learn a lot about the world. So in some sense, it's yes and no. But it doesn't mean that the world was created by a neural net. That's not the case. It just means the neural net is very useful for learning things in the world. Yeah. Okay. Yeah, so it's, again, philosophy class today, philosophy 101. Yeah.
So are you saying if you, like, instead of having a uniform hypothesis, if you have like some distribution which is like more narrow or something, I don't know, then does that like help you beat the disagreements through?
This is a very benign setting over there. They're like M, it's a finite number of examples, 0, 1 labels, uniform distribution. It's kind of, if you cannot solve that, what the heck are we doing? Right. It can be in the plane for all I know. These are nothing. This is a very benign situation. But let me add, unless there are more questions. Is it clear what I was saying so far? It's, again, mathematically, it's not sophisticated. It's, I would say, trivial even though you don't like me to say that. Okay, I take it back, not trivial, but it's not hard, what I showed you. But it's also not, there's nothing profound here. It's like more philosophical. You need to restrict the model a bit more. That's what I'm saying. So the solution that people came up with is to say, in addition to these, I have an hypothesis, an error, and a world, and a samples, and all that. There exists hypothesis class H that map X to Y. This is a family of functions. And I want to learn learnability is with respect to age. So examples of age, examples, linear classifiers, I'm not going to write what that is because you all know, right? You all know what linear classifiers are. Neural nets of K variables. And when I was born, we also had trees, decision trees, and various things like that. No one cares about that anymore, and for good reason. Okay. Good. So now, with this additional construct, I can now define statistical learnability, statistical or PAC learnability. It was defined twice, once in the statistical world and the next time by Valiant in '84 in computer science, but it's the same definition. And the definition, you'd imagine, two independent communities came up with such a bad model. How can that be? But here is the definition. So we say that learning problem given by x, y, c, h, anything else, that's it, is learnable if and only if for every epsilon delta bigger than 0, there exists an m that depends on epsilon and delta, such that exists algorithm that with m epsilon delta samples guarantees with probability at least 1 minus delta error AS, S is the sample, is less than epsilon. Yes, Elijah.
Sorry, what is n here?
Where do you see n? I don't see n.
Sorry, is that not an n?
I don't see an n.
There exists a
M. M.
oh m.
M. So
Okay, so
there is an
what is-
algorithm such sees m epsilon delta samples. This is samples. So
Oh, m. The number of samples is a function of
epsilon and delta. So for every epsilon and delta, there is a function that maps epsilon and delta to a natural number.
I see.
And then if I see that many examples, I can learn it with precision m and delta. Yes.
And this algorithm, you're saying it's restricted to the hypothesis class, right?
Yes. So, yes. So, and this is, well, it doesn't necessarily mean that, but yeah, let's say for now. So we can say that, how do I define it in a nice way? Yeah, so let's say A of S belongs to H. Now, you can extend this to, this is called proper learning. So the algorithm returns the hypothesis from the hypothesis class. If I wanted to learn a neural net, I do a neural net. If I wanted to do a linear classifier, I return a linear classifier. There's something called improper learning. That's going to be very important after the break. Well, we relax that. We don't necessarily insist that the algorithm returns the hypothesis, but then we will insist it competes with the best hypothesis in the class. It's kind of similar to regret in that sense. Yeah.
Do we know how many data points are there? Like infinite?
Yeah, it's a distribution. So you mean the support of the distribution?
Yeah. I guess it's finite number then.
No, you don't know that because the distribution is unknown. So, I should say that's part of the. Okay, good. I remember there was something missing here. So D. D is part of the learning problem. There is a domain, label, concept, hypothesis class, and distribution. Distribution is over x, y. I don't know nothing about it. All I know about it is I can sample a point from x, y. That's all my data access, like I wrote before. I'm not changing what I started off the lecture with. I can sample data this way. I don't know, I cannot, see the distribution probabilities, none of that stuff. I cannot do that. And this, its learnability needs to apply for any distribution over the data.
And the M, I guess, is universal.
The M is universal, yeah, exactly.
With respect to D.
To D, exactly. Doesn't depend on D. I could have more notations here, but I don't want to. I think this is fine. So the main construct that's learnable in this setting is the hypothesis class. Usually I say hypothesis class is learnable, from vectors and labels from vectors to 0, 1, or that's the kind of linear classifiers and so on. That's what I usually talk about learnability, because everything else is kind of implied. Learnability needs to work for any distribution. I'm not restricting it. For every epsilon delta, I need to be able to get the epsilon delta to 0, and there needs to be a finite. M is, by the way, called the sample complexity. So this is called sample complexity.
So do you care that is not the same algorithm for a given choice of epsilon and delta? It seems like most of the time you'd care that it's one algorithm that can adapt to.
Yeah, that's true. It should be, if I were to really be formal about it, it doesn't have to be, but usually it's the difference between uniform and non-uniform learning. The same goes for circuit complexity. It's kind of a similar situation. So is it reasonable that I will have for some epsilon deltas algorithm A and for others algorithm B? Not very reasonable. So usually I would say there is an algorithm that works for any epsilon delta. It's the same algorithm. But it doesn't have to be, strictly speaking. But I've never seen a situation where it's not. That's a good question. Yes?
Does it also for sampling with
Sampling without replacement. The definitions are pretty much are usually for kind of unrestricted sampling, because then it's not the same distribution. The distribution changes. Now, I don't think that's a big deal. So for continuous domains, you're never going to sample the same point twice. Probability 1. So that's kind of not a big hindrance. I think you can talk about both somehow. And it's not going to be very different. I'm defining it with replacement. Yeah. So it's a product distribution of a D. D doesn't change. The same D all the time. I can sample the same thing again and again. That's why I have this probability of failure. One of the reasons. Otherwise, there will still be probability of failure, but it's going to be more tricky. More questions? So now you can ask, okay, what can I learn with in this model? What is learnable? That was the foundational question of learning theory. What is learnable in this setting? And you can, by the way, what do you think? Is this a reasonable, if something is learnable, this model, and let's say M is small, is it a good? Does it really tell me a lot about the problem or not? What do you think? I mean, it looks like a nice thing. I see some samples and I'm able to generalize to the whole distribution. Yeah, Ben.
This at least just says that there exists an algorithm, but it might be very hard to find what that algorithm is.
Right. That's right. But I'm going to tell you a very general algorithm soon. But you're right. This is true. Could be difficult algorithm, could be inefficient, and so on. Right? Yeah, that's true. But let's say I have a lot of computational power. Then the statistics of it seems to be okay. Seems to be reasonable, I would say. You can learn with any distribution, any x, any y. It's kind of like a nice thing. Yeah.
I mean, maybe like your H is like not properly restricted to learn like something which does well, but maybe it doesn't represent like in the real world what's actually happening.
Oh, you're saying how does my hypothesis class, the approximation error, how does my hypothesis class approximate the real concept? That could be very far off. Yes, but we saw it's necessary. So I even proved to you the no free lunch. So you need something. And we have very powerful hypothesis classes, neural networks. They're pretty good. They can approximate almost everything. There are even theorems about it. Universal approximation, they can approximate any function, and so on. I would say that's not a huge restriction. Yeah.
It's a pretty good model, but I think the biggest issue with it is the fact that D needs to be fixed. And in practice, distribution shift becomes the biggest problem. And in lots and lots of applications, distribution shift happens significantly.
Well, the point Elijah is making, which I think is a very good point, is that distribution being fixed and sample IID from it is problematic. I would disagree on that, actually. I would disagree on that. So I would say, you can almost always say, I mean, you're probably thinking of LLMs. Is that what you're thinking of?
Yeah, or even portfolio selection, right? You could have regime changes and then your statistical model is losing money.
Yeah, but a common model for the market is the Black-Scholes model. That is geometric boundary motion. And that is statistical, and in fact, it's stationary, and you can incorporate non-stationary effects into it. So even there, I would say much of options pricing is built on Black-Scholes. A lot of finance is built on that, and that's totally within statistical assumptions. So even though there are deviations from it, probably they're not that significant. That would be my, yeah, Bogdan?
There is no guarantees about like rate of growth of M. So basically like if
That's right.
M is very large.
That's right.
it's very
Okay,
fast.
that leads me to, so you could say maybe the sum complexity is huge. Okay? Okay, let me prove to you something. And then I will remove that objection. And then in the meantime, you folks will think about other objections. Okay? So let H be finite. I think it's not a huge restriction. For example, all neural nets with weights that have some precision and they have, maybe 1,000 parameters. Or all Python programs that have 10,000 lines of code and each line is no more than 10 words. So I think it's not a huge restriction. It can be very expressive with a finite world. Any complaint about the finite? No complaint, right? Okay, so let's H be finite. Theorem. H is back learnable with M epsilon delta being 1 over epsilon squared times log H plus log 1 over delta. Maybe 1 sec, maybe less than equal to, maybe let's take here 4 or something. Okay, yeah?
Is that the cardinality of H?
Yes. But please allow me not to put the lines as well. Okay, when I say H, it's cardinality. So, Bogdan, this is not too bad, okay? So every finite H, I can learn logarithmic in the size. Logarithmic is great. Even if I have 2 to the 1,000, it's going to be 1,000. It's not so bad. See 1,000 examples, I know the thing. 1 over epsilon squared, also not horrible. In fact, let me give you, I'm going to do 1 over epsilon. Let me do that. It's not going to be a hard thing. And log 1 over delta, how can you, amazing. Yeah?
But what about neural networks? Suppose like each weight
Yeah.
has like quantization, like I don't know, 2 values, suppose 0, 1, like very.
Let's do the exercise. Let's do the exercise. What's the precision? B float 16? B float 16. B float 16. So you have 2 to the 16. How many bits is that? 2 to the 16? How many weights do you want?
Well, it's 1 million.
1 million. I'm going to give you more. Let's do...
1 trillion.
No. Let's 100 million. You can do some interesting stuff with 100 million. Okay? So times 100 million. So how many parameters? How many neural networks do I have with 100 million parameters? Each number is 2 to the 16. So it's like 2 to the 16 to the power 100 million. Yeah? Okay? Log of that, not too bad, I would argue. So 100 million. So I need to see 100 million examples. This is a huge, this is like a transformer, right? So I would argue it's not at the end of the world to do that. But let me give you even a bigger, also they are constrained. The weights are constrained. They're not really, they sum up to 1, the batch normalization, blah, 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 blah. Let me give even more striking thing. So let's say age is Python programs. Python code. That's a hypothesis. I give it an example. Here, Python, take the image, give me the classification. Okay? And let's say that you need like 10K words. So 10K words, you can write a lot of things in 10K Python code. And it's not like the vocabulary there is not 200K. The vocabulary there is kind of small. Maybe you have 10,000. I don't know how many words you have in Python. Less, maybe, 1,000, right? So 1K to the 10K, take the log, you're back to around 10K. So with 10K examples, you can learn Python code. You don't need a lot of them. Yeah.
Is there a connection here to like information theory and like common law complexity?
I'm just saying a trivial thing. You sound like you're saying some complex points, and I'm saying a very trivial thing.
Never mind.
Okay? Yeah. This is a very, I'm going to prove it to you. I have only like 10 minutes. How much time do I have? And I'll be able to prove it to you in the remaining 10 minutes. Yeah, Joshua.
Oh, I was just thinking, I feel like this framework might be like not good in the sense that you might not have a lot of problems that you can actually learn.
No, I claim it's the opposite. I claim I can learn everything. That's the, but let me show you that. So let's prove. So my algorithm is going to be pick sample S from D to the M. And then I think Rafael, you always wanted the power M. That's what bothered you before, the product. Okay, so pick S from D to the M. And then let's say S is, I will pick the size later. And then return H from H. Such that the error of H subscript S, this means the error on the sample. So this is the probability. If I pick X, Y from the sample, H of X not equal to Y is 0, and return it. This H. So what does my algorithm do? It picks a sample, then it finds a hypothesis that has error 0 on the sample, and returns it. And it says, okay, I think this will generalize, and that's going to be my solution. Is the algorithm clear? Why can I find such an H that has 0 error?
It's just finite.
Sorry?
It's just finite.
It's finite, that's right. And also my concept, I'm assuming my concept belongs to the hypothesis class, okay? So this means there is a concept that belongs to my hypothesis. So this is assuming it's realizable. So assume concept is in H. Otherwise, of course, I cannot do it. Yeah.
So about the concept class being, or the concept being an age, right? You said that you were going to restrict the hypothesis class so that you couldn't overfit by memorizing your data set, right? But what if the concept relies on memorizing the data set?
Let's get back to it today. I want to finish the proof, and then I'll get back to your question. Okay. So let me prove that. Now, I want to analyze the probability that my algorithm fails. And I want to say this is a very low probability. It's less than delta. What does it mean that my algorithm failed? It means this is the probability over the sample. The only random variable here is the sample. There is no other random variable. Okay, that's the only random variable I have. Yeah, everything is deterministic. Right? So what's the probability that my algorithm fails? Well, this H, the A of S, has error on the sample, that's 0, and the error of A of S on the real world, the generalization error, is actually bigger than epsilon. Do you agree? That's what it means I failed. Because if the generalization error is smaller than epsilon, I didn't fail, I succeeded, wonderful. And by definition, I always pick someone with error 0 on the sample. I always do that. So I need to go over all possible hypotheses, so this is equal to, or less than equal to, summation over all age in my class, probability that age is A of S, and the error over sample age is 0, and the error of age is bigger than epsilon. And why can I say this inequality when I sum up over all possible ages, that particular hypotheses? I can remove that. Why can I sum up over all individual ages? Sorry? Yeah, I mean, I'm considering a bigger event. So the event that my algorithm found a hypothesis that has 0 error and actually its generalization error is big, it means it found that some hypothesis, that hypothesis has 0 error on the sample and large generalization error. And maybe there are many such, I don't know, maybe there are many such hypotheses, but I can bound the union of events by the sum of their probabilities. Yeah, it's called union bound, yeah? Everyone okay? So this is what? This is equal to, I have here age, cardinality age. Now, the error of this age is bigger than epsilon. But what's the chance it will make an error on the sample? So this is the product over all x in S, x, y in S, that this age errors on x and the probability that age of x is 0 and error of age more generally is bigger than epsilon. So why can I take the product here? They're independent, exactly, right? How do I pick samples? I draw them independently from D. I don't do any, there's nothing dependent here. It doesn't depend on the hypothesis, doesn't depend on nothing. Every time I draw a fresh sample, that's my data access model. So this is age times, well, the error is bigger than epsilon. What's the chance I didn't make an error? It's at most 1 minus epsilon, right? So it's not bigger. So this 1 minus epsilon to the power m. M times this happened, product. Every time by some miracle, I drew someone that he didn't make an error on, even though he has error bigger than epsilon. So that happens with probability at most 1 minus epsilon. This happens m times. So this is bigger than delta for m, which is 1 over epsilon times log h plus log 1 over delta. If you want, I can make it a bit more detailed. So this is less than h e to the minus epsilon m. And here you can see how I got this. Yeah.
Is that hx equal to 0 or is it equal to what?
Sorry?
Is that hx equal to 0?
Yeah, you're right. Not age equal to 1. Yeah, correct. Thank you. Yep. Some other question here? So, yeah, that's it. That's the proof. It's a very simple proof. Yeah?
Why would you assume that H has no error in the sample? And
Oh, that's my algorithm. Look, my algorithm finds a hypothesis that has no error on the sample. I pick the algorithm. I'm allowed to pick the algorithm. Yeah. So I'm not going to pick a hypothesis that was terrible on the sample. And clearly, that's not a good idea. So my algorithm does something mildly intelligent. It kind of looks at the sample and picks the best one there.
Because just like a lot of the time, you don't want to, like that would be overfitting, that performs perfectly.
It's overfitting if I don't restrict my hypothesis class. If I do, it's perfect. Yeah, that's why I restricted my hypothesis class. Okay, this would break down. You can think what would happen if we didn't. If I didn't restrict my age, this log age would go to infinity.
And why do we want the concept to be part of the hypothesis class? Like, isn't that kind of a restrictive thing?
It will work even without that, actually. I'm not going to go into that, but even if it's different, you can pick the best. It's called agnostic learning. Looks like I'll have to go into that next lecture, but agnostic learning means I do the best in class and compete with the best in class. So the guarantee will not be error less than epsilon. It will be error of my algorithm compared to the best hypothesis in the class is going to be at most epsilon. That would also work. There was some other question here? Colin, you had a question? So, well, actually some good points were made here. Let me say what they are. Is next week break or we have another week? We have another week, right? Okay, because I didn't say everything I wanted to say. Somehow time was running short today. But some good points that were made. So what if C doesn't belong to H? Then we say that we can agnostically learn, if error of our H, of our algorithm, is at most the minimum H in H, error H plus epsilon, probability 1 minus delta. That's an extension. It works if I believe that my hypothesis class is a good approximation of the concept, and then I can try to get something like that. And what I showed you can do slightly more sophisticated probabilistic argument, but also trivial, also easy. That it's also like minimizing error on the sample is a good idea. So I did want to say one more thing, which I think I might have to push to next week, because that's an interesting connection between this statistical learnability and Onan convex optimization. But before I do that, let me summarize today's class. And my question to you is, why is the question of learnability, basically I showed you, I resolved it for you. So I didn't show you, but this number of samples here is tight. So log 1 over epsilon, log 1 of H, plus log 1 of delta. That thing is tight, you cannot do any better. And agnostically learning, there is 1 over epsilon squared, and that's also tight. And I claim that question is actually not the correct question. What is learnable in statistical learning theory is not the correct question. And you can ask why. Because basically everything is learnable. I can do a finite hypothesis class of finite Python programs or neural nets. These are great approximators to the world. Great approximators, we all know that. And what you see here is that I don't need too many samples and everything is learnable. Every single concept, doesn't matter what, it belongs to C or very close to C. So every concept I can think of is pretty much learnable in terms of packed learnability or statistical learnability. Do you agree? But then what's the caveat? What's the caveat? Why isn't this always, why don't I always learn statistical learning theory? Yes?
This might be just an instance of the non-static distribution argument, but I think another way of phrasing it is, last lecture we talked about games.
Yeah.
And then with this paradigm, we have no hope of doing well in games or any strategic settings or any settings where you are directly.
For sure. For sure, this doesn't handle adversarial environments, game playing. For sure. Many other beautiful things that we'll see doesn't handle yet. But still, I mean, if I just care about learning, I don't care about games. I want to learn, the world. Yeah, Joshua?
Maybe it's hard because maybe it's hard to find a constructive approach to develop an algorithm.
Very good. There is no algorithm. So So the conclusion from statistical learning theory, it's learnable. Great. How does it help me? What I did is I found the best hypothesis that maps to the examples that I saw. So fitting a neural net, maybe you can do that in practice, but it's basically NP-hard. It's an NP-hard problem if you have nonlinearities there. Fitting a Python program to examples, good luck. It's a very hard problem to solve. So there is no algorithmic consequence to this learnability, which renders it, in my opinion, much less interesting than a framework that already has algorithms built inside of it. And you can argue, okay, I know that's learnable this particular configuration. I get a method, and I can apply my method to learn whatever I want to learn. So to the YouTube audience, I've been kind of harsh on statistical learning theory today. But this is what I believe. So prove me wrong. Give me a counter argument. I'm happy to hear. I go by the science. Okay, so I'll see you all next week, Tuesday.